Welcome viewers, this lecture is on eigenvalues and eigenvectors. The lecture includes eigenvalues, eigenvectors, methods for obtaining eigenvalues and eigenvectors, characteristic equation and Cayley-Hamilton theorem. We start with the definition of eigenvalues. For this we consider a linear operator which is a linear transformation from Rn to Rn. Let us say A, which is n by n matrix associated with this transformation. Then the real number lambda is called an eigenvalue of the matrix A if there exists a non-zero vector x in this Rn such that Ax is equal to lambda x. So, every non-zero vector x satisfying this equation Ax is equal to lambda a is called an eigenvalue of A associated with the eigenvalue lambda. The eigenvalues are also called proper values. Sometimes we call them characteristic, or some texts call them latent values. The eigenvalues and eigenvectors occur in pairs. For a given lambda, there are associated eigenvectors. So, for a given lambda, there exists a non-zero x satisfying this condition, then lambda is an eigenvalue and x is the eigenvector of the matrix or linear transformation or linear operator A. From this, we can say that x is equal to 0 always satisfies 1, but it is not an eigenvector, because by the definition we have included those values of x which are non-zero. So, x is equal to 0 may be satisfying this equation, but it is not an eigenvector. However, lambda is equal to 0 may be an eigenvalue corresponding to this equation, and lambda is equal to 1 is an eigenvalue of identity matrix. Like if you write down lambda is equal to 1, this equation becomes Ax is equal to x. So, such a relationship is possible when A is equal to I, and that gives us the result that lambda is equal to 1 is an eigenvalue of identity matrix. Further, every non-zero vector in Rn is an eigenvalue of I associated with lambda is equal to 1. So, when I have Ix is equal to x, then whatever value I assign to x, this equation will be satisfied. So, I say every non-zero x will be an eigenvalue of I. If lambda is an eigenvalue and corresponding eigenvector is x, then one can establish that Rx is also an eigenvector corresponding to the given eigenvalue lambda. One can easily prove this. Let us say lambda is an eigenvalue, that simply means there exists x such that Ax is equal to lambda x, and this implies if I multiply both the sides by a scalar r, then r times Ax is nothing but A times Rx is equal to lambda times Rx, and that simply establishes this result. Now, we start with the equation Ax equal to lambda x. Rewriting equation 1 as Ax is equal to, I am writing x as Ix, so it becomes Ax equal to lambda Ix. Then I take this on the other side, then it is Ax minus lambda Ix is equal to 0, or I can say it is A minus lambda I times x is equal to 0. So, this is nothing but a homogeneous system of n equations, because A is n dimensional. So, this is a homogeneous system, and this homogeneous system will have a non-trivial solution. Why I am talking about non-trivial solution? Because I am interested in x is equal to 0, x is not equal to 0. So, lambda being an eigenvalue, we should have a non-trivial solution which is possible only when determinant of lambda I minus a is equal to 0. This is the result which we have discussed earlier. So, this homogeneous system will have a non-trivial solution under this condition. So, this gives me the scalars lambda which will satisfy this equation. So, the eigenvalue of A will be the scalars for which the matrix A minus lambda I is singular. I can write down this determinant lambda I minus A is equal to 0 in this form. One can notice that in this determinant each and every term, the term in the diagonal, they are of the form lambda minus A11, lambda minus A22 and lambda minus ANN. This is because of the fact that I am writing lambda I minus A. So, only the diagonals are affected, and because it is minus A, so all these elements will become negative. So, when I expand this determinant, then I can use any row or column. Let us say I use this column, then it is lambda minus A11 multiplied by this determinant. So, one factor is lambda minus A11. Then I can of course have terms corresponding to this, but if I consider this particular term, then this is again a determinant of order n minus 1. So, one more term like lambda minus A22 will come, and that way we will be having terms like lambda minus A11 multiplied by lambda minus A22 multiplied by lambda minus ANN. So, we will be having n such factors, and that means this equation when expanded will be a polynomial of degree n. So, we say this determinant which is a polynomial in lambda and it is of degree n. So, this characteristic equation is a polynomial in n, and since it is a polynomial of degree n, so f lambda can be written in this form lambda raised to power n plus C1 lambda n minus 1 plus Cn. This polynomial is called the characteristic polynomial, and since it is a polynomial of degree n, so it will have exactly n roots. These roots may be distinct, means that all of the roots may be different, or some of the roots may be repeated. If a root is repeated k times, then the eigenvalue is said to be of multiplicity k. So, we call it repeated root if k is less than equal to 2. So, if there is if all the roots having multiplicity k is equal to 1, then the roots will be distinct. So, if k is equal to 1, then eigenvalue is a simple eigenvalue in that case. Now, one can observe that if I put lambda is equal to 0, then determinant minus a is equal to coefficient Cn, and if determinant a is 0 or the matrix is singular, then Cn will be 0, and that means my characteristic equation will come in this form lambda raised to power n plus C1 lambda n minus 1 plus Cn minus 1 lambda. The last term will be missing from here, and this means I can take lambda outside and we can have lambda multiplied by polynomial of degree n minus 1, and that simply means that lambda is equal to 0 is an eigenvalue of the matrix A. So, if determinant A is 0, then lambda is equal to 0 is an eigenvalue of the matrix A, or lambda is equal, if the matrix is singular, then lambda is equal to 0 will be a root of the characteristic equation. Therefore, we have the following result, and we can write down in the form of a theorem that an n by n matrix A is singular if and only if 0 is an eigenvalue of A. I have proved one part, but the detailed proof can be taken up later on. The set of all solutions to this equation is called the eigenspace of A corresponding to the characteristic value lambda. As I told you that this will have number of solutions. So, all the solutions will form an eigenspace. corresponding to a value lambda. The eigenspace is a set of all eigenvectors and 0 vectors. Mind here, 0 vector is not an eigenvector, and without 0 vector it will not be a eigenspace or a vector space. So it is important that eigenspace is the set of all eigenvectors and a 0 vector. The eigenspace of A is the kernel of this matrix lambda I minus A. Now we have discussed the meaning of eigenvalues and eigenvectors, but now we will discuss the procedure for finding eigenvalues and eigenvectors for a given matrix A. So the first step towards this is that we form the matrix lambda I minus A for the given matrix A and then calculate its determinant, equate it to 0, and then we solve this equation. As I told you that this is polynomial of degree n. So solution of this equation means finding the roots of this equation, and depending upon the value of n we will be having number of eigenvalues. So let us say the eigenvalues are lambda 1, lambda 2, lambda n for A to be an n by n matrix. It has to have n roots. Some of them may be repeated, but the total number of roots will be n. Now for each lambda I, we solve the system lambda I minus A x is equal to 0. So we put this value lambda 1 here and we solve this equation. This is a system of equations. This simple equation actually represents system of equations. So if A is n by n, so there are n such equations. There will be n simultaneous equations, and this is the matrix equation, and this equation is to be solved. The solution of the system gives the eigenvector associated with the eigenvalue lambda. So let us illustrate this procedure with the help of examples. So in the first example, I am considering a 3 by 3 matrix 4 minus 1 5 0 6 0 1 minus 2 0, while in the second example I am considering a 2 by 2 matrix. So first the matrix A as this, the first example. So according to the method which I have illustrated, I have to first obtain the solution of this characteristic equation. So the characteristic equation is determinant lambda I minus A is equal to 0. So I substitute this value of A in this equation. So the characteristic equation becomes lambda minus 4, because it is I means only diagonal terms will be affected. So lambda will appear in the diagonal only, and because of minus A all these terms are negated here. So 4 here, so it is minus 4 minus 1, so I have 1 here, 5 the corresponding term is minus 5, 0 this is minus 6, and 0 1 becomes minus 1, and we have 2 and lambda. So this determinant equal to 0 is the characteristic equation for the given matrix A. So this is the characteristic equation, this is to be solved. So what I am doing here is, let us consider that we expand this along this column. So it is lambda minus 4 multiplied by lambda minus 6 into lambda multiplied by minus 5 into lambda minus 6. So this is the characteristic equation. So when we expand this determinant, we will have this characteristic equation which can be simplified. So if these two terms are multiplied, we will have this expression, and then minus 5 lambda plus 60 plus 30 is equal to 0. Further simplification will give me a cubic polynomial. It is a 3 by 3 matrix. So we expect characteristic polynomial to be a cubic polynomial. So we have lambda cube minus 10 lambda square plus 19 lambda by combining these two terms plus 30 is equal to 0. So this characteristic equation is to be solved. So we factorize this equation. So lambda is equal to minus 1 is a factor of this equation. So we take it out this factor, and what remains is this, and simplifying this we will have lambda plus 1 lambda minus 5 into lambda minus 6 equal to 0, and this gives me 3 distinct eigenvalues as -1 from this vector, this 5, and from this vector 6. So, this 3 by 3 given matrix has 3 eigenvalues -1, 5 and 6. So, once we obtain eigenvalues, the next step is to obtain eigenvectors. So, we have to obtain eigenvectors corresponding to each of the eigenvalues one by one. So, I start with lambda is equal to -1. So, for this I have to form this matrix equation A minus lambda I x is equal to 0 and lambda is equal to -1 in this, and A is this given matrix. So, if I substitute this A and this lambda is equal to -1 in the given equation, I have -5, 1, -5, this will be negated, and 0, -7, 0, -7, 2, -1 multiplied by x1, x2, x3 is equal to 0, 0, 0. This 3 by 3 system is to be solved, and to solve this homogeneous system, I will form the augmented matrix for this system, and it is -5, 1, -5, 0, -7, 0, -7, 2, -1, the coefficient matrix here, and this column is appended here. And then I like to apply linear transformation so that this can be reduced in a diagonal form or in an echelon form. So, this can be made 0 by suitable linear transformations, and this matrix reduces to this matrix. And from this I can further apply linear transformations, and what I have is 5 -1, 5, 0, 0, 7, 0, 0, and in fact I can have I can multiply this by 9 and this by 7. So, after subtracting this will become 0. So, one row becomes 0 in this augmented matrix, and by this we can say that rank of the matrix A is 2, and from rank nullity theorem, nullity is equal to 1, and that means the solution vector of A x equal to lambda x is the eigenvector, which can be obtained as -k, 0 and k. So, nullity is equal to 1. So, what can I do is I can write down the third in the third equation. I can write down the third variable as k. Then this equation will automatically be satisfied for y is equal to 0, and by writing y is equal to 0 and z is equal to 5 will give me x is equal to -1. So, this is a solution for the given equation, and we will have in fact infinitely many solutions of this equation, and each solution will be represented in this form. K can take infinitely many values. So, we will be having all the solutions will be of this particular form. So, we can say this is the basis for the eigenvectors associated with lambda is equal to -1. Once we have solved this problem, then we go to the next eigenvalue, lambda is equal to 5. The same steps can be repeated. That means, we again start with the matrix equation A minus lambda I times x is equal to 0 for the given matrix A, and then we form the augmented matrix. We apply linear transformations in series, and once this matrix is reduced to the echelon form, which is this in this particular example for lambda is equal to 5, and one can notice that again this row becomes 0, and that means rank of this coefficient matrix is 2 and nullity is equal to 1. And in that case, if you solve this equation, this system of equation, k can be taken arbitrary value, y can be 0. So, when we substitute it here, this is k is arbitrary k and this is 0. So, x becomes 5k. So, the eigenvector corresponding to the eigenvalue lambda is equal to 5 will be of the form 5k 0 k. So, eigenvector. The third eigenvalue was lambda is equal to 6. Again the whole thing is repeated. a minus lambda I into x is equal to 0 for this given value of a. The augmented matrix is obtained first. We apply elementary transformations, and this time these elementary transformations lead to this matrix. Here this row becomes 0. So again the rank of the coefficient matrix is 2, but the nullity is 1 for lambda is equal to 6, and that means we can write down the solution of this matrix as, if we say x3 is arbitrary, then y becomes minus 7 by 5 x3, and we substitute x3 as x3 here and minus 7 by 5 x3 here, then this can be, x can be obtained as 16 by 5 x3. That means x, y and z, they are written in terms of the component x3, or let us say x3 is equal to k, then this can be written in the form 16k minus 7k and 5k. So this vector is an eigenvector corresponding to eigenvalue lambda is equal to 6. So we have 3 different eigenvalues in this example, and we have obtained 3 different eigenvectors in this case. In the next part, we have been given a 2 by 2 matrix. So we apply the we have to first find the characteristic equation. So we write down lambda minus 5 1 minus 1 lambda minus c, determinant of this is equal to 0. We solve the determinant, lambda minus 5 into lambda minus 3 plus 1 equal to 0, and this gives me lambda square minus 8 lambda plus 15 and 1 16 equal to 0. This equation gives me lambda minus 5 lambda minus 4 whole square equal to 0. So this case gives me lambda is equal to 4 is an eigenvalue and its multiplicity is 2. So it's a case when the eigenvalues are repeated. So when the eigenvalues are repeated, then you have to solve this augmented matrix to obtain the eigen vectors corresponding to lambda is equal to 4, and one can notice that this row is the same as this row. So rank of this matrix is 1 and nullity is also 1 from the rank nullity theorem. So nullity is also 1, and that means it has only one linearly independent solution which can be obtained from the homogeneous system. So although the multiple root is 2, but we have only one eigenvector corresponding to the eigenvalue lambda is equal to 4. So in the earlier example we had 3 distinct values and we got 3 eigenvectors, but in this case we got we got repeated eigenvalues and we have only one eigenvalue corresponding to that. So what is that eigenvector corresponding to lambda is equal to 4? It is k and minus k. Now we will establish some results related with eigenvalues and eigenvectors. So let us say A is a square matrix of order n with eigenvalues lambda 1, lambda 2, lambda n. Then determinant of A is the product of eigenvalues. Now to prove this, let us say a square matrix of order n. Then the roots of this characteristic equation determinant lambda I minus A is equal to 0 are lambda 1, lambda 2, lambda n is being given to us. Then since there are roots and this is a characteristic polynomial of degree n, so we can write down that characteristic polynomial which has roots lambda 1, lambda 2, lambda n as the product of this. So we can say determinant lambda I minus A is equal to lambda minus lambda 1, lambda minus lambda 2 and the factor lambda minus lambda n. Now in this case, if we put lambda is equal to 0 in this, then determinant minus A is equal to this minus, this minus, this minus. These lambdas are put to 0. So there are n minus signs. So we will have minus 1 raised to power n, lambda 1, lambda 2, lambda n, and this is equal to determinant of minus A. This lambda is put to 0. Now we know that determinant of minus A is equal to minus 1 raised to power n determinant of A. So, this minus 1 and this minus 1 will get cancelled, and we have determinant A is equal to lambda 1, lambda 2, lambda n. So, we have proved the result. So, the example which we have done earlier, we have obtained the eigenvalues as minus 1, 5 and 6. So, this was the matrix in that example. So, if we substitute, if we use this result, then determinant of A is the product of these eigenvalues. So, determinant of A is equal to minus 30. The next result is, if A is a triangular matrix, then the eigenvalues will be the diagonal entries A11, A22, An. Like, if A is a triangular matrix, so let us assume that it is an upper triangular matrix. The similar way the result can be proved for lower triangular matrices also. So, let us assume at the moment that A is a upper triangular matrix, then the characteristic equation will be this. So, since this is upper triangular matrix, so all the elements in the lower part is 0 and only these elements are non-zero. And then characteristic equation is lambda I minus A. So, we will have minus A11, minus A22 and so on in the diagonal terms, and we will have lambda minus A11, and all these terms will be simply negated. So, if you expand this determinant, it comes out to be lambda minus A11. Now, we are expanding this determinant along this column. So, lambda minus A11 into this determinant, and rest of the terms will not contribute anything because they are 0. So, lambda minus A11 into determinant this means lambda minus A22 into this determinant and so on, and that means it is lambda minus A11, lambda minus A22, lambda minus An. So, this is an nth degree polynomial and all these are factors. So, if it is 0 means all these factors have to be 0, and that means lambda is equal to A11 is one eigenvalue, lambda is equal to A22 is another eigenvalue, lambda is equal to An is the nth eigenvalue of the given matrix A. What are A11, A22, An? They are nothing but the diagonal elements in the given matrix A, and that was to be proved in this theorem. So, this result is particularly important because to solve an eigenvalue problem, one has to first obtain the characteristic equation, and that means this determinant is to be obtained. Finding the nth degree polynomial corresponding to the given matrix, if you have to expand this determinant, is really difficult, and then finding eigenvalue and finding the solution of that characteristic equation is further complicated. But if we can have a lower triangular matrix or upper triangular matrix, then you do not have to worry about rest of the elements. You can simply write down the eigenvalues as A11, A22, An, the diagonal elements. So, this result helps us in finding out the eigenvalues of matrices. There is one more result. It states that V1, V2, Vn be the eigenvectors corresponding to n distinct eigenvalues of lambda 1, lambda 2, lambda n respectively, then V1, V2, Vn will be linearly independent. So, if V1 is an eigenvector corresponding to lambda 1, V2 is an eigenvector corresponding to lambda 2, and Vn is the eigenvector corresponding to lambda n, then these vectors are distinct if these vectors are linearly independent if these eigenvalues are distinct. So, this is the theorem. So, let us prove this result. So, let us say that lambda 1, lambda 2, lambda n are distinct eigenvalues corresponding to a given square matrix A, and lambda 1 and V1, V2, Vn be the eigenvectors. Then we can prove this result by induction. So, we start with V1 is an eigenvalue corresponding to lambda 1, so only one vector, so it is always linearly independent. The next we assume that V1, V2, Vn minus 1 corresponding to different lambda 1, lambda 2, lambda n minus 1 are linearly independent. Then we have to prove that when Vn is added in this linearly independent set V1, V2, Vn minus 1, then the complete set is linearly independent. So, to prove the linear independence of this set V1, V2, Vn minus 1, Vn, let us consider the linear combination C1 V1 plus C2 V2 plus Cn minus 1 Vn minus 1 plus Cn Vn is equal to 0, and if we can prove that these C1, C2, Cn minus 1 and Cn are all 0, then we can say that these vectors are linearly independent. So, we apply a linear transformation A to this. A is a matrix. So, let us multiply this equation by matrix A, and since it is a linear combination and A is a matrix, so we can say C1 into A V1 plus C2 A V2 plus Cn minus 1 A Vn minus 1 plus Cn A Vn, and A multiplied by 0 is 0. Now, since V1 is an eigenvalue corresponding to since V1 is an eigenvector corresponding to eigenvalue lambda 1, so A V1 is equal to lambda 1 V1. So, that is we are replacing A V1 by lambda 1 V1. Similarly, A V2 is to be replaced by lambda 2 V2, as lambda 2 is the eigenvalue and V2 is its corresponding eigenvector. Similarly, this term will become lambda n minus 1 Vn minus 1, and the last term will be Cn lambda n Vn equal to 0. Let us call this equation as 2. Then multiplying the equation 1 by lambda n and subtracting from 2, what we get is, this is multiplied by lambda 1 and we multiply this by lambda n, subtract from this. So, what we will have is this equation C1 V1 is common, and this is lambda 1, but this is being multiplied by lambda n and subtraction is taking place. So, it is lambda 1 minus lambda n V1 plus C2 times lambda 2 is coming from here and lambda n from here. So, it is C2 times lambda 2 minus lambda n V2, and we will have all factors up to these terms, but when you see this last term, it is Cn lambda n Vn, and this is also Cn lambda n Vn. So, these two terms will be cancelled out. So, we will have terms C1 up to Cn minus 1. Now, given that all the roots are distinct, that means lambda I is not the same as lambda n. For any I 1, 2 to n minus 1, lambda n is different than all these lambda i's. So, they are not 0, and further V1, V2, Vn minus 1 are linearly independent, and that means this is equal to 0. This is not 0, this is not 0, this is not 0, this is not 0. So, the sum of this linear combination is 0, simply means that C1, C2 and Cn minus 1 has to be 0, because V1, V2, Vn minus 1 are linearly independent. So, C1, C2 and Cn minus 1, they are all going to be 0. So, when we substitute these values in 1, then we have the expression Cn Vn is equal to 0. Vn is not 0, it is given to us, it is a vector which is non-zero. So, what we have is that Cn is equal to 0 is the only alternative. So, we have obtained a linear combination which is 0 only when C1, C2, Cn's all are 0, and that proves that V1, V2, Vn will be linearly independent. So, if we have n distinct eigenvalues, then the corresponding eigenvectors will be linearly independent. So, this was the theorem. Now, if the characteristic root lambda of a matrix A is repeated k times, then A may have k independent eigenvectors. It may happen, it may not. If all the values are distinct, definitely will have independent eigenvectors, but if they are not distinct, they are repeated, then the corresponding eigenvalues will be dependent or independent. Both the things are possible. We have discussed an example in which A is a 2 by 2 matrix, 5 minus 1 1 3. We have obtained its eigenvalues as 4 and 4. So, the eigenvalues are repeated, and we could find only one independent eigenvector in this example as k minus k. So, for the roots repeated, we got only one eigenvalue. However, if we consider A as this matrix, then the characteristic equation is determinant lambda I minus A x is equal to 0, gives me this determinant equal to 0, and when you solve this determinant, the characteristic equation comes out to be lambda lambda minus 1 equal to 0. That means this is a singular matrix and it has an eigenvalue 0. This result we have already established, and the matrix A has a repeated eigenvalue 1. So, it has 3 eigenvalues 0, 1 and 1. So, if we consider the repeated value lambda is equal to 1, then lambda I minus A x is equal to 0 is to be solved for lambda is equal to 1, and to solve this we consider this augmented matrix, we apply elementary transformations. Let us say this and this row has to be added. So, this will become 0 row. So, this matrix has 2 0 rows. So, the rank of the coefficient matrix comes out to be 1 and nullity is 2, and this means the solution of this system is 0, r and s. See, any value 0, r and s will satisfy this equation, and we write down x is equal to 0, y is equal to r and z is equal to s will also satisfy this equation. So, any solution will be of this form. Any solution of this system will be of this form. Now, this involves two arbitrary constants r and s. That means there are two independent vectors as a solution of this system. They are 0 r 0 and 0 0 r. So, in this example we have a repeated eigenvalue 1 with multiplicity 2, and when we solve for eigenvectors for corresponding to this eigenvalue, we find that there are still two independent eigenvectors associated with the given matrix. So, I have taken two different examples where in one example there is an eigenvalue which is repeated, but we could get only one independent vector, and in the another example there are two independent eigenvectors associated with an eigenvalue of multiplicity 2. So, if the roots are distinct, we are sure that the vectors are going to be independent, but if the if the roots are not distinct, then we cannot say the vectors will be independent or not. They may be independent in some examples, in some other examples they may be dependent. Now, another theorem, it says that the eigenvalues of a matrix is the same as its transpose. So, that means if I have a matrix A having some eigenvalues, and if I take the eigenvalues of the corresponding transpose matrix, the eigenvalues of the two matrices will be the same. So, let us consider the characteristic equation for A transpose. So, it is lambda I minus A transpose is equal to 0. Then lambda I minus A transpose can also be written as lambda I minus A transpose, because I is a symmetric matrix and determinant will not be affected. So, we can take determinant of lambda I minus A transpose is equal to 0 as simplification to this, and this means lambda I minus A is equal to 0 because determinant of this and determinant of this they are same, and that means we have same characteristic equation for A as well as for A transpose, and that means their solution will be the same, and that implies that the eigenvalues of A and its transpose will be the same. This is another property of eigenvalues and eigenvectors, and according to this, let lambda be an eigenvalue of A, then lambda square is an eigenvalue of A square. To prove this, let us say lambda is an eigenvalue and x is its eigenvector. So, Ax is equal to lambda x is given to us. I pre-multiply this equation by A. So, it is A times Ax is equal to A times lambda x. Since lambda is a scalar and matrix multiplication is associative, so left hand side becomes A into A x is equal to, right hand side becomes lambda can be taken outside from the right hand side, and the right hand side becomes lambda times Ax, and that means A square x is equal to lambda times Ax, and x is equal to lambda x being given to us, we can have A square x is equal to lambda square x, and from here one can say that lambda square is an eigenvalue of A square. So, lambda square is an eigenvalue of the matrix A square. This is to be proved. Then the next theorem says that if lambda is not equal to 0 is an eigenvalue of a non-singular matrix A, then 1 upon lambda will be the eigenvalue of A inverse. The same lines we can prove this result. So, we say that lambda is an eigenvalue of A, that means Ax is equal to lambda x, and x is not equal to 0 because this is the equation for determining lambda, eigenvalue lambda and eigenvector x. So, x is not to be 0. For lambda not 0, we can write down this equation as 1 upon lambda Ax times x. For lambda not 0, A is non-singular. This is being given to us. A is non-singular, so lambda is not 0. Therefore, A inverse exists. For non-singular matrix, A inverse exists, and we can multiply this equation by A inverse. So, we will have 1 upon lambda multiplied by A inverse Ax is equal to A inverse x, and A inverse A is identity. So, 1 upon lambda into Ix is x is equal to A inverse x, and from here one can conclude that A inverse has an eigenvalue 1 upon lambda. Now, we say that if lambda is equal to 0 is an eigenvalue of a matrix A, then A is singular. To prove this, let lambda is equal to 0 is an eigenvalue of A, and x is not equal to 0 is an eigenvector associated with lambda. That means Ax is equal to 0 into x is equal to 0. So, this system Ax is equal to 0 will have a non-trivial solution if and only if A is singular. This is the result which we have already developed, and this proves that lambda is equal to 0 is an eigenvalue of a matrix A, then A is singular. Now, let us consider this expression. Determinant lambda I minus A times identity matrix is equal to adjoint of lambda I minus A multiplied by lambda I minus A. This result we have already developed. Now, this lambda I minus A, its determinant is a polynomial of degree n, when this multiplied by I is a matrix equation, is a matrix expression, and we can write down this determinant lambda I minus A as an lambda n plus an minus 1 lambda n minus 1 plus an minus 2 lambda n minus 2 plus a1 lambda plus a naught. It is a polynomial of degree n. Each term in adjoint lambda I minus A, this on the right hand side, is a polynomial of degree n minus 1 in lambda. Why? Because in the adjoint matrix each term is a determinant, and determinant of one order lower. So, it is a polynomial of degree n minus 1 in lambda. So, we can write down adjoint of lambda I minus A is equal to Bn minus 1 lambda n minus 1 plus Bn minus 2 lambda n minus 2 plus B1 lambda plus B naught. What we have done is that we have written Bn minus 1 as a n minus 1 order square matrix. Bn minus 2 is a n minus 1 order square matrix. So, each term is written separately. So, we write down this adjoint lambda I minus A as this expression. Here B naught is identity. Then determine lambda I minus AI is equal to B naught lambda n minus 1 plus Bn minus 2 lambda n minus 2, last term happens to be B naught, multiplied by lambda I minus A. Now, what we can do is, on this side we have a polynomial expression lambda I minus A, this is multiplied by matrix I, and here also we have polynomial terms lambda n minus 1 lambda n minus 2, and they are multiplied by matrices. So, let us equate terms related to lambda raised to power n and its various powers. So, if I compare coefficients of lambda n, then on this side it is A naught I, A n I, and on the right hand side it is Bn minus 1, Bn minus 1, and this is multiplied by lambda I. So, this becomes lambda raised to power n. So, on the left hand side I have A naught I, that is the coefficient of lambda n in this characteristic equation, and on the right hand side we have Bn minus 1. Secondly, lambda n minus 1. So, on the left hand side I have A n minus 1 I is equal to, from here I will be having two terms, one corresponding to this, another corresponding to this. So, we will have this term. Similarly, other powers. So, we have this expression. Now, if I multiply the first equation by A n and this equation by A n minus 1, and then I add. So, what will happen? This is A naught n, this is A raised to power n, and here I have Bn minus 1, Bn minus 1, this is An minus 1, this is being multiplied by this. So, this is An minus 1, and here also have A. So, this becomes An. So, if this way if I multiply each and every term and add, then this term will get cancelled with this term will get cancelled with the other terms, and this term will get cancelled with this. So, if I add these expressions, then we will have A naught A n plus A n minus 1 A n minus 1 plus A n minus 2 A n minus 2 and so on, A1 A plus A naught multiplied by I on the left hand side, but on the right hand side will not have any term. In fact, all the term will get cancelled. So, this equation is obtained, and this is equal to 0. This is a matrix equation equal to 0. So, this is the characteristic equation which we had, A naught A n lambda n plus A n minus 1 lambda n minus 1 plus A1 lambda plus A naught equal to 0, and what we have obtained is A n plus A n minus 1 multiplied by the matrix A raised to power n minus 1 and so on. So, if you compare these two expressions, what we can say that this lambda is replaced by A. So, if this is the characteristic equation, then the matrix A will satisfy its own characteristic polynomial. So, this is the result which we have, that a square matrix satisfies its characteristic polynomial. Now, this is an important result, we call it Cayley-Hamilton theorem. Let us illustrate this result with the help of this example. So, find the characteristic equation for the given matrix A and verify the Cayley-Hamilton theorem for this matrix. So, let us say A happens to be 1 2 1 0, simple 2 by 2 matrix. For this we can find the characteristic equation, determinant lambda I minus A equal to 0, as this determinant equal to 0, simplify this determinant, it is lambda times lambda minus 1 minus 2 equal to 0, and lambda square minus lambda minus 2 equal to 0 is the characteristic equation for this given matrix. So, according to Cayley-Hamilton theorem, this matrix A satisfies its characteristic polynomial. That means A square minus A minus 2 is equal to 0. So to prove this, let us compute A square. A square is this matrix A multiplied by A. So if you simplify it, it is 1 plus 2, that is 3. 1 into 2 is 2. This is 0. And similarly, when you multiply this row by this, we will have 1. This row multiplied by column is this 2. Substituting the values of A square and A in the matrix equation, A square minus A minus 2i gives 3 2 1 2 minus the matrix A minus 2 times identity is equal to 0. You can check 3 minus 1 minus 2 is 0, and similarly other terms, and we will have A square minus A minus 2i equal to 0. So we have proved in this example that matrix A satisfies its characteristic polynomial. We can use this result for finding the inverse of a given matrix. So if we start with the characteristic equation, lambda n plus a1 lambda n minus 1 plus a2 lambda n minus 2 and so on, and we write down the corresponding matrix equation according to the Cayley-Hamilton theorem. We will have a n plus a1 a n minus 1 plus a2 n minus 2 and so on equal to 0. Then multiply this equation by A inverse if it exists, then it is A inverse is pre-multiplied equal to 0, and then this A naught multiplied by A inverse I is this term on the left hand side, rest of the terms are taken on the other side. So we have an expression involving A inverse in terms of powers of A. This can be used for finding A inverse. Let us illustrate this with an example. So find inverse of given matrix A using Cayley-Hamilton theorem. A is 1 2 1 0, which is given to us. It is a 2 by 2 matrix. So we first find its characteristic equation, which we have obtained as in the case of earlier example, lambda square minus lambda minus 2 equal to 0. Then the corresponding matrix equation according to Cayley-Hamilton theorem is A square minus A minus 2i equal to 0. We substitute the value of, we pre-multiply this equation by A inverse. So we will have 2A inverse is equal to this, two terms can be taken on the other side, is A minus I. So we can substitute the value of A and I in this equation, and this gives me A inverse as half this minus this 0, 2 minus 0 is 2, 1 minus 0 is 1, and 0 minus 1 is minus 1. So this is A inverse. Let us verify that we have got the right result. So we say A into A inverse is equal to half into this 1 2 1 0 multiplied by the inverse 0 2 1 minus 1 is equal to 1 0 0 1. So A inverse comes out to be identity. I have tried this example with pre-multiplying this equation by A inverse, but the same result can be obtained if you multiply if you perform post multiplication, then again you will get the same result. To summarize, we have discussed eigenvalues, eigenvectors, characteristic equation. We have discussed a method for finding eigenvalues and eigenvectors of a given matrix. This method depends upon evaluation of determinants. Finding determinant is not a simple problem. In fact, we have to develop more methods for finding eigenvalues and eigenvectors for a given problem. We have already discussed Cayley-Hamilton theorem. We have discussed how to use Cayley-Hamilton theorem for finding inverse of a given matrix. With this, we come to the end of the lecture. Thank you.
Thank you.